Okay, so in this video, I'm going to be going through the Yuhua Secondary School Electronics prelim paper. So, courtesy to one of my guys to doing this paper. Um, oh yeah, and I like this like embellishment thing. So, thanks. I don't know if I can say your name, but thanks. Okay, there we go. Alright, so let's just get through it. Oh, before I continue, right, before you continue the video, I highly suggest you go ahead and try this paper yourself first. Apologies for the weird scan. We just got it like this, so nothing much we can do about it. Alright, so let's see how you did. Fixed DC voltage source, ground, buzzer, Zener diode, microphone, LDR. Yeah, this is alright. Okay, 6 marks. Figure 2.1 shows capacitors. Okay, so this is just effective capacitance. So yeah, this would be 150 plus 390. Then we would have them in series, and then you do this to you do this plus then this one will be which will be equals to 1 over C effective, which you've done. So if you've calculated it correctly, then you're right, and you have, so good. The voltage V3 across capacitor 3 is 8 volts. Calculate the charge. Okay, yeah, so it's just using the equation. Yeah, yeah, C is Q over V. Farads is charge over voltage. So you just plug in the thing and you should get it right. But you don't? Oh, Q is C times V. Oh, okay. You get, yeah, sorry, you don't get anything. So the correct, wait, no, am I dumb? Yes, okay, thank you, you're welcome. Wait, so why did you get it wrong? 180 times 10 to the power, but it's C3. What? This is, where do you even get? Oh, you took C. Oh, you took the effective capacitance. Oh, that's a shame. Yeah, okay, that's nothing. Sorry. The 150 microfarad capacitor has a tolerance of plus minus 10%, highest value. So you just take 150 plus 10% of 150, which is 165. So you're right. Okay. Complete 3.1 by converting each measured value. Okay. So I'll do like two. I'll do two here, okay? So for, let's say, 6.8 microfarads, right? The way you do this is for micro. Okay, wait, I drew that a bit. For micro, we're actually going to move to convert it to remove the prefix, right? We're going to move the decimal point to the left, and then we're going to do it a number of times. So for micro, right, it's actually times 10 to the power negative 6. So we're going to move this decimal point to the left 6 times. So 1, 2, 3, 4, 5, 6. That's it. Then the decimal point is here now. Then this will be 0. And then each loop here, right, where is going to be a 0. So 0.0000000000068. Yeah, and then the decimal point is not here. So this is right lah. Then but this is for a prefix that has like negative power lah. Then what about a prefix of positive power? So this is times 10 to the power of 3, right? So in this case, we're going to move the decimal point to the right 3 times. So 1, 2, 3. So now it's here, and then we're going to have 1600.0 or 1600. So this is right lah. Let me check if I'm not just saying like BS. I am not. So okay, yep, 4 marks. Wait. Yeah, 4 marks. Okay. In the answer key, right, it says 0.150. And technically here you're not wrong, because 0.15 is equals, okay, when I say 0.15 it means like 0.15 lah. It's equals to 0.150. But this is something to do with SF. So basically here, oh, but that's the thing though, because this is actually 2SF. So technically here there shouldn't be a 0, but the answer key says there's a 0. So I don't know what that. Yeah. Okay, yeah, alright. Next. 4.1 shows an electric kettle used to boil water at home. Why did it tell us the weights? Okay. Calculate the energy used by this electric kettle. So energy is P times T, and this is P. And then time is in seconds. So yes, you convert 4 minutes to seconds by times 60. So this is it lah. And if you calculated that right, which you have, then you get a mark. So yeah. Oh, thank you so much for highlighting the answer. That's nice. The efficiency of the electric kettle is 65%. Calculate the amount of useful output energy. So 65% equals to, ooh. Okay, I have a few issues with your working here. I wouldn't suggest putting the percentage sign because right, if you were to actually, let's say, okay, you just take your calculator right now, right, and then you just type in 100 and then put the percent sign, and you see that 100% is equals to 1. Why is that? So we can actually, basically, right, percent is actually equals to this. It's not necessarily, oh, but he wrote it on both sides, so it's valid. Because technically they cancel out. Okay, fair enough. My second, okay, then ignore what I just said. Yeah, I don't think there's anything useful from what I said, so you can just ignore it. The second gripe that I have is that you did not show your preliminary steps to get 234,000 joules. So like in here, for instance, right, you actually say, oh, okay, P is 1,500. Oh, okay, T is 60 times 4. I showed a conversion. In this case, you just immediately jump to here, which I don't really like. I would have preferred if you went, oh, okay, 65 times this, oh, is equals to 100 of useful output energy, then blah, 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 oh, then 235,000. I would have preferred that. If in the answer key they do show the preliminary steps, I may not be able to give you the full marks, but let's see first. They do. Okay, no, I'll just give you, but just that's something to note for you guys watching. So just always show your calculation steps. Calculate the current flowing through the electric kettle. So we know the power, we know the voltage, because 230, and then we know that P is VI. So again, just plugging in the values. 6.52, yeah, okay, nice. Figure 5.1 shows a carbon resistor. So this is just using the table to get the resistance values, and that's just like basic pattern recognition, so I'm not going to go through that. Did you get it though? Yes, you did. Yes, you did. Okay. Okay, if you think about it, right, they're asking you to determine the resistance of the resistor. Oh, but the resistance is plus. Okay, yeah, I was thinking maybe this is not needed, but now that I think about it, no, just have it included. So yeah, okay, you got this right. Maximum current through this resistor is expected to be 50 microamps. Determine a suitable power rating. Huh. R is VI, so we know the voltage in it. And then we know the power because P equals VI. Yeah. There's actually instead of, okay, wait, let me just see if you're right first. Yes, you're right. So basically, this is one way you can do it, but you can actually, right, instead of using P equals VI, you can actually use P equals I squared R, and it means the exact same thing. And then now instead of needing to do this, right, you can just plug in the values without the need of V. But you do get the mark lah. Just saying. In the exam, I'll probably done what you did because I that's just the way I do things. But if like as a time killer, yeah, maybe this is I mean this is an alternative lah. Okay, but what you did wasn't wrong. In fact, it was right. Okay, so this is KCL. Okay, I will go through this question actually. So KCL states that the current going into a node is equals to the current exiting the node. So using this, right, we can actually get the current here. So let's look at I1 now. Okay, so I1, we can see comes out from this node, and actually, we can see that a current is going in, a current is going out, and that's it. So there's only 3 currents interacting with this node. And for 2 of those currents, we actually know the value. So we pretty much have an equation, and we can just find I1. So current entering a node, which is 5 amps, is equals to current exiting the node. So exiting will be I1 plus 2 amps. So we can just find I1, which is 3 amps lah. And then you do the same for everything else. That is quite simple. And if you've done that correctly, which you have, then you'll be good. So good. Whoa, this thing is like scoliosis, bro. Alright, there's an AC wave. Describe the function of a digital oscilloscope as a type of electronic test equipment. It is used to observe waveforms. Yeah, I think that works, but maybe a better way of saying it is like to observe a signal as time progresses or something. Yeah, it is used to observe how the voltages at different points of a circuit change with time. I don't think I can give you the mark for this one, sorry. Okay, you know what? I've seen many people make this mistake countless times. This is a chapter 15 thing, so I guess I'm compelled to make a video on it. So you can go ahead and check that out. State the peak-to-peak voltage of this signal trace. So the voltage from here to here. And then that'll be 10 volts lah. So this is right. Say the DC level, the level at which the signal oscillates around. So it's 0 volts. Time period 500 milliseconds. Yeah, so from here to here is one pattern. It repeats itself again. That's why it is this is one period, and then it takes 500 milliseconds for that. So this is right. State 2 differences between AC and DC. Direct current flows in one direction only, but alternating current changes direction periodically. Let's put a pin in that. I'm not sure about the usage of the word direction, but let's see. The source of direct current comes from batteries, but the source of alternating current comes from AC generators. I don't know. I don't know if I like that answer. Okay, flows in one direction, whereas okay, so you're right. You're actually word for word here. Okay, what about the other one? Polarity of DC source does not change, whereas the polarity of an AC source changes periodically. Polarity and direction are different. Okay. Yeah, okay. So now I guess it's based on my own judgment and jurisdiction to see if I think you deserve the mark for this. The source of DC comes from batteries, but the source of AC comes from AC generators. Yeah, I don't know if that makes the cut. Because right, it I would bring it off as a little vague. So you say that the source of DC comes from batteries, but you don't say that AC does not come from batteries. So I have to assume now. Because now it's just like you're listing examples. And you're not saying, oh, but actually AC can only come from a function generator or whatever. So I don't think I'll give you the mark for this. And is this a bit of a nitpick? Yes, but I have to be nitpicky because I need to go through every single possible point. Why is this page bigger than the second page? So yeah, I cannot give you the mark for this point, unfortunately. Why is this bigger than everything else? It's just this. What? Okay. 8.1 shows numbers in various formats. And then complete the table. Okay. So this is just okay, yeah. This may be a bit much. I don't want to eat into too much time. Eat too much time off my current time of time. So I'm just gonna check the answer key. Yeah, you are good. So I'm not going to explain how this works now. I recommend watching the video that I have on this if you are unsure on how this works. State one advantage and one disadvantage of using BCD to binary. Advantage: BCD is useful for displaying decimal numbers. That's true, I guess. BCD disadvantage: BCD needs extra binary bits to give the same number, while binary does not. I think you're right on both. Yes, you're right on both. So you're right on both. What I recommend is, instead of saying binary bits, just say bits. What? This, okay, I guess I'm wrong then. Okay, please go on to say binary bits. Okay. Yeah, okay, good. Alright. Okay, and then there's section A. So before I move on, right? Let me get a grade or sum up your marks for section A before we move on. So 6 plus 3 plus 1 plus 4 plus 2 plus 2 plus 2 plus 1 plus 2 plus 3 plus 1 plus 1 plus 1 plus 1 plus 4 plus 2. So in total you have 36 out of 40, which is good. Okay, why did I say 60? You have 36 out of 40. Very nice. And 60. Alright. So let's see how you're gonna do for section B. Did I skip it? Yes, I did. Oh shit, okay. Let's see how you did for that. Wait, let me drink a bit of water first. Okay, figure 9.1 shows a full wave rectifier circuit. The simplified diode model consists of an ideal diode connected in series with a battery. The simplified diode model consists of an ideal diode, one ideal diode. Oh, the simplified whoa, what am I talking about? I was, in my mind I was like, this rectifier only uses one diode, but I'm just stupid lah, basically. Never mind. So it's saying that the simplified diode model consists of an ideal diode connected in series with a battery, and is often used to describe the behavior of a diode in a circuit. Cool. Explain the function of the battery in the simplified diode model. It is to supply current for the ideal diodes. I don't know about that. The battery represents the forward voltage of, yeah, no. Sorry. So you have to specifically say that the battery is to show the forward voltage of a diode. Alright, so yes. Give one benefit of using the simplified diode model instead of a practical diode. The simplified diode model does not have a breakdown voltage. I mean, technically the breakdown voltage is negatively infinite lah. What does the answer key say? Quick analysis of a circuit, easier to use. Yep, no, this is wrong. So you had to say either it is to perform a quick analysis, or that it's easier to use than a practical diode model. And many analyzers do not need such a high... Oh, and because usually it's mainly for analysis. You would rather use this than a practical diode model, since the simplified diode model is more effective and simple to use in circuit analysis. That's the real reason. Alright, cool. Explain how this converts AC to DC. Alright, so let's see how you do this. When current flows through point A, the current has two directions, D, being forward biased, and D1 being forward biased, and D4 being reversed biased. I don't like this statement at all. because current has only one direction. Current flows like this, right? Let's say, okay, so let's say we have a battery now, or okay, let's say we have an AC source, and then we have this. So I'm replicating this now. Let's say current flows like this. This current has one direction. In the next phase of AC, it goes like this. Current still only has one direction. So I don't know if I really like this statement here, but I will probably ignore it. So let's see what happens. D1 being, and then it causes D1 to become forward biased, and it causes D4 to become reverse biased. Therefore, current will flow in one direction, okay, through. Oh, no, 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 no. Oh, you mean, when it gets to point A, it can go either here or here. But because this is in reverse bias, this is in forward bias, therefore, it goes here. Okay, I see what you mean now. I see what you mean. So it it will flow in one direction through D1 as current flows easily, showing a conversion of alternating current to DC. Okay. When current flows to B, through B, the current has two directions. Again, it has choices. It can go either here or here. But because D2 is in reverse bias, it will not go to D2. Being reverse bias and a pathway for current to flow to D. Oh, whoa, the English is so ass. Wait. D2 being reversed biased and a pathway for current to flow to D. Yeah, the English is bad. Hence, current will flow in one direction and not go the way of D2 as it resists more current, showing a conversion of alternating current to D. Yeah, that's not going to cut it. So all you said pretty much, right, is that, okay, let me just sum up what you just said. What you said is that current will flow here, current will not flow here, it will go here, current will not flow here, it will go here. And then you said, therefore, AC is not into DC. So I no. No. Okay, during the positive half of the input, D1 and D3 are forward biased and act like closed switches. However, D2 and D4 are reverse biased and act like open switches. And as such, the current flows from AB to DC. Yes. And then I suppose we can see the opposite when it's in the negative half of the input. Now D2 and D4 act like closed switches, and D3 and D1 act like open switches. And as such, the current will flow from CD from CB to DA. Okay. During the negative half of the input, a current still flows through the load resistor in the same direction as the positive half. So basically what that means is during the positive half, during the negative half, either way, current still comes out at B and flows through the resistor. And because of this, the output always remains positive. The output always remains positive, regardless if the input is negative. So you have to explain it like that. So how the marking scheme awards marks is it first said during positive, when it flows like this, when it flows like this, flows like that. That's what you have done here. Then it does it again for the negative half, which you have not done. Then it sums up, oh, in both positive, negative, right, it comes out at B. So because of that, I can only give you 1 mark. It's okay, you learn something every day. Calculate the time period for the circuit in 9.1. So frequency is 12.5 hertz, and then we can just use this equation. Yeah, so it's plugging the values, and you got it. Nice. Complete 9.2 to show the waveform of the input voltage. So we know that 1 period is 0.08 seconds, which is equals to 80 milliseconds. Yes. We also know that, okay, where does it, oh yeah, it's 9 volts. Okay, so peak to peak voltage will be 18 volts or peak voltage will be 9 volts. That's pretty much it There's nothing else to talk about that. And you got it, so good. Complete 9.3 showing the waveform of the output the output voltage using the simplified diode model with a forward voltage. Okay, so now, yes, 7.6, because basically in the positive half of the input voltage, in the negative half of the input voltage, the current always flows through two diodes. It is unavoidable to go through one only or to not go through. You have to go through exactly two diodes. And because of this, since we know that a diode has a forward voltage, each diode, right, will actually take a little bit of that voltage to power itself, basically. And since we know the forward voltage of one diode is 0.7, and we know that the current goes through 2, so we can find out how much voltage is lost. Why do we need to find out how much voltage is lost? Because voltage is lost. And as such, the output voltage will not be at 9 volts. The peak voltage will not be at 9. Some voltage is lost, and then now we know that lost amount. So it will be 9 minus the total forward voltage of the two diodes, which you have done flawlessly here. And then something that people usually screw up is they do this. This is wrong because these two waveforms here are actually not going to connect. Because what we're doing is we are having, okay, the old waveform was like this, right? Okay, it was not. The old waveform was like this. Then we flip it up, but now it is at peak 9 volts. So we need to bring it down. The thing is, when we bring this down, it does not, this part here is actually going to be at the bottom, and as such as spacing here. So this spacing is very important, so don't miss that, guys. But it looks like you got it, yeah. Why is yeah, okay, so you got it. 3 marks. Okay, let me remove my shit that I added. Yep, 3 marks, nice. A component can be added a component can be added into 9.1, so here, to smoothen the DC voltage. State the name of this component, capacitor, yes. Explain how the component smooths the DC voltage. The capacitor can charge and discharge the circuit, so it will allow smoother flow of current. Yeah, no. Nope. Okay, as the capacitor takes time to charge and discharge, the voltage across it will not be able to follow the fast changing output of the rectifier. This causes the output voltage to vary over a much smaller range. Okay, this is wrong completely. So what you need to state is, yes, the capacitor will charge and discharge, but you have to add the point that it will take time to charge and discharge. Let me show you why that matters. Okay, let me show you why that matters. Let's say we have, this is an input voltage. Let's say this is the input voltage, and then let's say we have a capacitor. If the capacitor were to charge and discharge instantaneously, that means it takes 0 time to charge and discharge, the voltage across the capacitor, or the output voltage, will mimic the input voltage. Does this look smooth to you? No. But let me propose a different scenario. What if it took time for the capacitor to charge? If it did, it would take time to charge, and then once, as a fact when the voltage goes to 0 or close to 0, the capacitor will start discharging. So now we are here because this part is actually charging the capacitor, but now we are in this down part. Since the capacitor takes time to discharge, it's not going to jump all the way to 0. No. It's going to go down a bit, but it can't discharge all the way because immediately it's the next charging cycle. And then it does this. And watch and marvel at the fact that now the output is smooth. So it is important to state that the capacitor takes time to charge and discharge, because if it did not take time to discharge and charge, then it would just mimic the input voltage. There will be no point. It will not smoothen. So for this, I cannot give you a mark at all. Okay. 10.1 shows a DC motor connected to a transistor. Okay. And then there's just some, and the current rating is 100 milliamps for the motor. The motor has a current rating. That's interesting. Okay. Alright, let me drink some water. Alright, this is very funny. So, is known to all of us. Basically, this is, as this guy has so beautifully written, this is actually the current gain of this transistor. But people always think that the current gain has a unit. It doesn't. The unit of the current gain is nothing. There's no unit. It's just like radians. There's no unit for radians. It's not like centimeters, So, um, yeah. Oh, wait, but you drew the arrow from unit, so I don't know if... Okay, it's fine. Um, explain... Okay, it uses a DC motor. Explain explain why this DC motor could damage the transistor. When current flows through the DC motor, a magnetic field is produced. Oh no, okay. Since there is no diode... Okay. Since there is no diode, the magnetic field in the motor will produce a large negative voltage spike each time the motor is switched off, damaging the transistor. So are you saying when there is a diode, the magnetic field will not produce a large negative voltage spike? Because if you are, that's wrong. So, okay, wait. And then secondly, I'm not sure if... Okay, the reason why this person has stated magnetic field, if you did not know, is because in a motor, the motor is pretty much an inductor. And a property of an inductor is that when you drive a current through it, a magnetic field is actually produced. Once you stop driving a current through the inductor, the magnetic field will collapse and produce a large negative voltage spike. The thing is, I don't know if that's the appropriate explanation for this question. It is! Whoa! What? Oh, it is! Okay, alright. Okay, wait, what? What does the answer key say? When a current flows through a DC motor, a magnetic field is produced. Okay. Yeah, you get 1 mark. So, the reason why you get 1 mark is, again, because you say since there is no diode, the magnetic field in the motor will produce a large negative voltage spike. So that means if there is a diode, then the magnetic field will not produce a large negative voltage spike when the motor's turned off. But that's not true. So you're just wrong. Okay, anyway, next. Funny, man. So, okay. Draw on figure 10.1 a diode that will prevent damage to the transistor. Yeah, okay. So we just draw the diode in reverse bias to the battery because when the magnetic field collapses, it will produce a negative voltage spike, and this diode eats it all up. So yeah, this is correct. The transistor has just saturated. Okay, that's a stupid way to say that. Anyway, calculate the voltage across the DC motor. Your answer must include units. What kind of statement is that? Your answer must include units. Okay. So the transistor has just saturated. That means that VCE is 0.2 volts. So this is 0.2 volts. And right now what we have is, we can just simplify this. We have the motor. We have this thing that takes up 0.2 volts, and then we have ground. Using KVL, we know that the sum of voltages inside a series circuit is equals to the supply voltage. So we can just use some basic math here to find the voltage across the motor. So 9 minus 0.2, 8.8, you're right. Calculate the base current required to operate the DC motor at its rated current. Your answer must include units. Why do you keep telling us to include units? Alright, anyway. So, for the DC motor to operate at its rated current, the current going through the motor has to be 100 milliamps. And we know that current in a series circuit is equal. So, if Oh, and this is this part here is the collector. So if the current at the collector is 100 milliamps, the current going through the motor is 100 milliamps. And we're asking for IB. And we know how IC and IB relate to each other. We can use IC and IB to find current gain. And we know the current gain. With all these variables that and facts set in place, we already know what to do. So all we need to do is set IEC to 100 milliamps. Then we can just use the voltage. Okay, HFE is current gain if you guys didn't know. And then we just set, then we just state, okay, DC current gain is equals to IC over IB, which we should know. It's just a fact. And then we can just rearrange stuff, sub in values, and we'll get it. So 100 divided by 40, which is 2.5. It's not 2.5 lah. It's not 2.5. Okay, but 100 milliamps. Okay, fair enough. Yeah, 2.5, nice. Alright. Using your answer from here, calculate the value of RB. RB, okay. So again, this is just applying equations that we already know. So RB is V in minus VBE divided by IB. Okay, what does this mean? Now, okay, a little known fact. This part here highlighted. I didn't even notice there were these highlights, but okay, Control Z is not working. Alright, this part highlighted in pink, unless you're colorblind, is actually acts as a diode. Just a little fact. So let's simplify this right now. We have 5 volts in here. We have this resistor RB. We have a diode, and we have ground. And then they're asking for the value of RB, which is asking for the resistance. So we know VBE. We know VBE, the diode, is 0.65 volts, or the forward voltage of the diode is 0.65 volts. Again, as I already stated here, using KVL, we know the voltage across this. Okay, we do. Do we know the current? Oh yeah, we do, because the current is IB. Again, current in a series circuit is equal, and we know IB. Wait, why am I pausing? Yes, we know IB. So, we know the voltage here, KVL. We know the current here, which is IB. And guess what? Ohm's law exists. R is equals to VI. And then that's it. We're just plugging in values. So, yeah, 5 minus 0.65, 2.5 milliamps, and then you convert. Be sure to show your conversion of the prefix, which you have kind of done here. I would prefer if you had a preliminary step that showed 2.5 milliamps, but this is fine, I think. And then 1740. So are you right? Yes, good. Using your answer from this and this, calculate the power. So, okay, now you suddenly know how to use different equations. Okay, so yes, P is equals to I squared R, and it's just subbing in, subbing in values 10.9 milliwatts. Alright, so that's good. 11, entrance barrier, control flow of visitors into a hospital. That's funny, I just came back from visiting a hospital. After 5 people have passed, a lock is operated to close the barrier for 10 seconds. Also, it's like a chalk. Is it like a chalk? No, it's not like a chalk. Okay. Okay. Complete the circuit in 11.2. Add a push to make switch and a resistor. Okay, this is. Okay, this annotation is fine. I'm not saying anything. To provide a clock signal that will advance the decade counter. Ignore the need for a debounced switch. So okay, we're just making either a pull up or pull down switch here lah. A logic gate that will reset, clear the counter on the 5th count. Okay, so right now you have a pull up resistor. When your button is open, high voltage is going into the clear, into the clock. and when your voltage is and when your button is closed, then 0 volts will go in. So I forgot whether the clock changes on the falling or rising edge, and it changes on the falling edge. So good. And then logic gate that will reset the counter on the fifth count. So the fifth count will be equals to in binary will be equals to wait, let me just 0 1 2 3 4 5. So it's equals to 101. And we know that this is the least significant bit, and we know that's A. So it's just facts that we know. We just know that QA here is equals to the least significant bit. So now we know this is B, this is C. And what we can do is this, with this, right, is we can create a logic circuit to check. Oh, you messed up. You messed up big time here, buddy. Okay, so we can create a logic circuit to check whether CBA is 101. So why did I say you messed up? Is I say you messed up because this is wrong. You get 0. The reason the reason why is right now what you have. Let me just simplify. Right now what you have is A, B, C, and then you just have an AND gate here, and then your output lah. This works for some cases. We only want, okay, just to verify it, let me just make the what we are trying to do here clear. When CBA is 101, the output of this circuit here must be 1. Okay? So let's just try some values for the heck of it. Let's try 0, 0, 0. So 0, 0 is an AND gate, right? I'm not going to draw a truth table because if you're still need a truth table, you're gone. So 0, 0, output 0. So far it works. Let's try another one now. 1, 0, 1. Okay, I do not know why wait, let's try 1, 0, 0. So now we have 1, we have 0. Output 0. Now let's try 1, 0, 1. And then in theory this should produce 1, which it does. The thing is, we only want it to clear when it's 1, 0, 1. Okay, wait, now I'm starting to think that you're right. Okay, I see. Okay, you know what? I see what you're doing with this now. The reason why I thought he messed up is because it would also clear in a binary number like this. But I don't think that matters. Yeah, that doesn't matter. Hui! Oh, one step ahead, man. This guy definitely copied the answer key. So, this is right. Wow, I'm stupid. I was too quick to judge. Alright. Complete the timing diagram. Okay, so this is just... Alright. Falling edge, so A... This is A, so A, yep. And then everything else, yep, this is... Yep. I'm not gonna go through this at all. 14.4 shows the Firefly IC timing circuit used to provide 10-second delay to control the barrier lock. State the operation mode of the Firefly timer. So this just facts again. This is monostable mode. Monostable mode. Is there another way of saying that? Just monostable. Yeah, okay, this works. A falling edge is required to trigger the Firefly timer. Add a component to 11.4 to provide a suitable connection between the clear pin of the decade counter and the 555 timer trigger pin. This is right, but I think... Okay, but I don't know, this looks weird. Wait, is this right? A NOT gate is used to connect the clear, so it needs a NOT gate. So the reason why it needs a NOT gate is because for the signal here, it's gonna be 1 like this, and then our output here is gonna be like this. So at this instant of time, we want this thing to clear, but the thing is, it only triggers on a falling edge. So the counting bit clears here, but since this is a rising edge, it's not gonna trigger this. So here, when it falls, then it will trigger the discharge. But that's not what we want. We want this to be triggered at the exact moment that the clear pin goes from 0 to 1. And we can achieve that using this NOT gate, because now at this instant of time, the output of the NOT gate actually produces a falling edge. And then that triggers it at the same instant of time of this. So that's why you need a NOT gate. Using 470 microfarads for C1, calculate the value of R1. So yep, this is just plugging in the values into equation 19.3. Yep, okay, cool. The use of a mechanical switch such as a PTM switch is likely to cause contact bounce in the decade counter, yes. State what is meant by contact bounce and explain its effect on the operation of the process section of the system. So you just didn't even try that. Alright, so what is contact bounce? Can everyone right now pick up a pen or pick up a stick or a pen? Are you at a table right now? If you're at a table, good. Because I'm going to demonstrate what contact bounce is, right? Wait, can I turn on my camera in OBS? I use OBS, by the way. Can I add something into video capture device? 1080. Oh, it's not showing though. Oh, okay. Okay, yes. I hope you guys can see me. I don't know if this is actually gonna work, but so this is me. I have this marker here in my hand, and then I have this table edge. Okay, so what I want you to do is take this marker and go close to the edge, and then stop holding the marker, and then you see that the marker falls to the edge of the table, obviously. But listen, you don't hear one sound. You're not pushing the marker into the edge. You're lightly dropping it. You hear several bounces. So what do these bounces mean? That means when your switch, okay, let me just relate this back to the switch. Once your switch closes, that bounce is going to happen. Regardless of whether you push it in hard or whatever, it's just mechanics. There will be a bounce. That is what contact bounce is. Okay, I'm gonna turn off my camera now. That is what contact bounce is, alright? So, and then, okay, what is its effect on the operation of the process section of the system? So, when this contact bounce happens, it actually closes the circuit more times than you would prefer it to. Let's say you press once, right, but contact bounce, it actually opens and closes the circuit maybe 3-4 times. What happens for this, right, is your circuit or your switch is connected to something that increments a value. So instead of incrementing once, you're going to increment 3 or 4 times, and that's bad. So that's the effect lah. Okay, how does the answer key say it? So when the push to make switch is opened or closed, its contacts will connect and disconnect several times before a firm connection is established. This is known as contact bounce. Okay. The count value may increase by multiple times when we only wanted to increase by 1. Yep, perfectly said. I mean, directly lifted from the textbook lah, but perfectly said. Let's move on. Oh, that's nice. So 12.1 shows a factory and its system diagram. Toy bears are counted. And then stuff. 12.2 shows an incomplete circuit for the infrared sensor. And then complete the circuit. Photodiode that turns the output of the voltage comparator high Okay. Components that provide a reference voltage. A method of adjusting the sensitivity of the circuit. Okay. So outlook not good. I think you got 0. So let me explain why you got 0. First, a photodiode that turns the output of the voltage comparator high. A few things. Number one, you've put the photodiode wrong. So a little known fact, your photodiode actually is in reverse bias. Am I tripping? No. Secondly, you do not connect in your circuit here. What you've done is you have this diode, you have a resistor ground, and then you have power, and then you do this. So that's pretty much wrong. I don't know if you noticed, right? But what we're doing here is we're actually creating a voltage divider. So the way this photodiode works is that when you actually shine a light, not IR diode, you can actually just shine a regular light into the photodiode, or actually any LED for that matter. If you just take any LED and shine light into it, right, a small current is actually produced. That's just the more you know fact. And then what you can do with this is, because there's a small current that's produced, you can actually say, oh, there's a resistance. And then, voltage divider? Yes, that's what we're doing. So the wire placing here before the diode is wrong already. So two things are wrong with this bit here. The polarity, or the fact that your photodiode is not in reverse biased. And um, and the fact that your wire is before the diode. So that's wrong. Okay, so your wire should be like this. So this is wrong already. Components that provide a reference voltage 4.5. So again, that's voltage divider, and you have done it here. Two resistors, which in theory will divide the voltage to 4.5 volts. The thing is, right, friend, the resistance could be anything. So I think you need to specify resistance. You don't need to specify resistance, but you kind of have to. So I don't think I can give you the mark. And then a method of adjusting. Oh yeah, with suitable values indicated. So you don't get a mark because you did not provide suitable values. And then you just did not provide a method for adjusting the sensitivity of the circuit. So that lends you 0 marks, friend. Sorry. Oh yeah, and then yep, it's just yep. So yeah. So yes. Okay, let's move on. Table 12.3 shows the truth table of octal counter. Column X shows that the toy best selected for inspection are taken at the second, third, and sixth counts. State the SOP Boolean expression without simplification. So we just look at this, and then we look at the ones of the output, and then if we see, and then we just get each expression of that one, and then we have to add bars now. We add a bar when that variable is 0. So it'll be like this, it'll be like this, it'll be like this. And you got it. Using a K-map or Boolean algebra, simplify the Boolean expression. So you've chosen to use a K-map, and then you put in your values. So is this right? 0, okay, 0, 1, 1, yes. 0, 0, 1, 1, 0, 1, 0, yes. 1, 1, 0, yes. And then you grouped it up appropriately, because yep, you've grouped it up well. C is oscillating through 1 and 0, so take C, throw it in the trash. Here A is oscillating, so A bar B, B C bar, so this should be right. A bar B. Okay, yeah, that's right. Why didn't the answer key put Boolean expression or Boolean algebra? Oh, is it just that simple to simplify? It is, okay. Draw a logic circuit using AND, OR, and NOT gates. Okay, cool. So Wait, did you get it right? Oh, you did. Okay, let me just check if you got it right, and then I'll say, okay, yeah, you got it right. I don't like you that you did this. I don't know why there's 010, probably for testing purposes, but please don't have it there when you hand up your paper, man. Alright. So how did he do this? So it all boils down to the method lah, which I'll show you now. So what I recommend is first write down your inputs on the side. So A, B, C. Then write down your output on the opposing side. Now look at each expression. And then think to yourself, okay, how can I use logic circuits to create this expression? So for A bar B, first thing we can note is that, oh, A is being inverted. So we can just add a NOT gate lah. Then we see that A bar is multiplied with B. So they AND. Next, look at the other expression. B and then C bar. Oh, C is being inverted. Oh, B is being multiplied with the inverted C, which means AND. And then, now that we've looked at all expressions, we see how they correlate with one another. And they are added together. That means, add means OR, as you should know. Watch the video if you don't. We just OR, and then that's it. So the process is actually extremely simple. So yeah. AND, OR, and NOT gates can be constructed from universal gates. Really? Really, they can. State 2 reasons why the product manufacturers might want to use universal gates. Reason 1, universal gates would be more convenient than inserting many AND, OR, and NOT gates in the same circuit. That's true. NAND gates and NOR gates are efficient in constructing more... Okay, I don't know about that point though. Let's see what answer key things. All other logic gates can be built using NAND gates or NOR gates. That's a stupid point, man. NAND and NOR gates are economical and easier to fabricate. Universal gates would be more convenient than inserting... I think this point is correct. NAND gates and NOR gates are efficient in constructing more logic gates. That's not true. That's actually false. NAND and NOR gates are inefficient at constructing logic gates. Okay. Okay. Oh, is this repeated? Okay. Let me paint you a picture. Let's say we are trying to use the NOR gate to create some gates. So you say that it's more efficient in constructing more logic gates. So let's try. Okay, let's say I want to use NOR gate to make an AND gate. How do we do that? This is how you do it. This is how you do it. This is how you construct an AND gate with NOR gates. But you didn't say efficient in constructing logic gates. You said in constructing more logic gates. So let's have more AND gates then. So how would you construct this? Can I? Yeah, I can select. So, okay, why is that connected? What? Okay, can I unconnect them? Okay, I think you understand what I'm trying to say lah, okay? Oh, what is going on? What? I did not type this. I didn't type this. What does that even mean? Okay, I think you get what I'm trying to say. So this statement is just false. It is not efficient at all. It is cost effective though, but you have to do all of this crap just for this. And then if you want to do more logic gates, you got to do this again and again. It's just utter chaos lah. So I don't agree with this point. Alright, so yeah, this is 1 mark. And then I guess that's done. So let's tally up your marks. I went back too much. Okay, here. So 1 plus 2 plus 2 plus 3 plus 1 plus 1 plus 2 plus 3 plus 3 plus 3 plus 2 plus 2 plus 4 plus 1 plus 3 plus 3 plus 3 plus 3 plus 1. 43 out of 60. So in total, you get 79 out of 100, which is not that bad. Alright, and then I think, okay, I just started like really crazy. I think that's me being like half stingy. So 79 with me being half stingy is not too shabby, if I say so myself, friend. So, yes, that's it. And I think this concludes the video. So, thank you very much for watching.